Anyway, today I'm going to talk about Greenfield, the in-browser Wayland compositor that I've been developing for about over a year now, I believe. So, who am I? My name is Erik de Rijke. I'm from Belgium, so I'm basically presenting in my hometown right now. I'm self-employed. During daytime, I'm not really involved with anything graphics related, unfortunately. It's mostly Kotlin, a bit of Java, pays the bills, right? During the night, it's mostly JavaScript, C, basically anything needed to get stuff working. Now, what is Greenfield? It's a Wayland compositor, plain and simple. It runs in the browser. It's written in JavaScript, oh horror. But unfortunately, I did my best, I did my research. It's written in ES6 JavaScript, which means we have all the interesting stuff like classes, classes, lambdas, constants, all the good stuff. It uses one file per class, so it's not a single bloated file with 10,000 lines. It's nicely and cleanly structured. And it uses JS doc type comments everywhere. So at least we have some kind of type safety feeling, at least. It also uses WebAssembly, so for all the hard parts that are already solved on the native side, those libraries are compiled to WebAssembly and used inside your browser. Saves me a lot of time. So what does Greenfield offer? Well, it does not offer you a solution similar to VNC, RDP, or Citrix. We will soon see what it does offer. It's not something finished, so it's very much a work in progress. Still a lot of parts need to be finished, need to be polished. So what is it? Well, it's definitely something super awesome. I mean, I wrote it after all. It's pure JavaScript. There's a wee bit of assembly, as I said, and it requires absolutely no plugins. It's all HTML5. It's all standard JavaScript libraries. A bit cutting edge maybe here and there, but that should be okay. So what is it? Well, the main difference between your RDP and your Greenfield is it offers rendering of applications on a per application basis. So the difference with RDP or other solutions is that they create and they composite the screen remotely and then send you back the entire screen. Because Greenfield is actually a compositor, it creates the entire output inside your browser itself, and every application separately sends its frames to your browser to be displayed. So in essence what that means is that it's actually a true cloud desktop environment. Now I know cloud is a word with a lot of definitions, but for all intents and purposes it really is that. Your application, you don't need to care where applications come from or where they run. They just basically pop up on your screen, and they can even run on different hosts if you want. And yeah, it's definitely still a work in progress. Now, first some basic concepts explained. I guess most of you are already familiar on what Wayland is. For those who are not, Wayland is basically a display server, a window manager into one. It's the successor of X. It's a classic client-server architecture. It usually runs, well, it always runs on the same machine, except for this case, of course. And all communication in Wayland protocol happens through a binary wire protocol. The protocol itself is actually defined in XMLs. So you have a protocol generator, it reads the XMLs, and it outputs a stub library, usually then further implemented in libWayland client and libWayland server on the native side. It also offers you to send file descriptors over the wire. So instead of sending a huge chunk or a huge blob over the wire and copying it, it just creates a file descriptor, sends that. Basically gives you zero copy data transfers, much faster, obviously. It might be interesting to note that in Greenfield it also does support file descriptors. It does that, however, through a bit of special trickery called WebFD. Unfortunately, I do not have the time today to go into detail about that. If you want to know more about that, you can ask me after the presentation. A second important building block of Greenfield is WebRTC. Now, what is WebRTC? WebRTC is basically what is the browser's solution to video conferencing. WebRTC allows you to establish a direct peer-to-peer communication between endpoints, between browsers, but it doesn't have to be your browser. And it does that by they both agree on what would be the ideal form of communication, and next a direct peer-to-peer connection is established. So any further communication between peer A and peer B will be a direct link, and there is no intermediate in between. And this basically allows browsers to directly communicate with each other without the central server interfering. And this is also extensively used in Greenfield. So, how does it work, Greenfield? Well, on the right side we have a general picture of the architecture. It's interesting to note that the signaling server is actually inside this little cloud, as well as the server that serves your static HTML and JavaScript. Let's go over it together. On the top we have our browser compositor. So this is basically the end user's browser machine that you can see. And the browser compositor at the top is built on Westfield. Westfield is a separate underlying library. It's also written in JavaScript. And it basically functions as the protocol generator, which I explained earlier. It generates all your stubs based on the Wayland XML files. You can use vanilla Wayland XML files. There's no modification required. And those stubs are then implemented by Greenfield in the browser. At the bottom, we see application endpoints. Now, what are application endpoints? Application endpoints run on your remote hosts. They're basically daemons. And they function as a proxy compositor for which a native application can connect to. So when an application endpoint is initially started, it announces itself to your browser compositor, or rather to an intermediate, and then to a browser compositor once it's connected. And it creates a separate child process for each browser tab that is connected. It creates a separate child process which functions as a proxy compositor. Which means that once a Wayland application connects, it connects to this proxy compositor, and all communication is forwarded through WebRTC, which I just explained, with a direct connection to your browser. So the intermediate server is not involved in any way when the transportation happens. The application endpoint is written in Node.js. Was mostly done because I was quite familiar with it to get quick prototyping. It's not, obviously, not the most performant piece of code. So ideally, yeah, I guess rewrite it in Rust or something, I don't know. It also uses a fork of libwayland server. The reason for that is that it needs direct access to the wire protocol, which is now mostly hidden in Wayland server, and we need that direct underlying wire messages so we can forward them to the browser. It also encodes application frames. So once an application wants to transfer frames to your browser, it's a bit silly to transfer the whole raw image over network. That would be quite slow. So we want to encode that, compress that, and before we send it, so it's smaller. And that's also done by the application endpoint. The application endpoint, as stated, uses WebRTC. You could also use WebSockets. The WebRTC implementation was done because it was relatively easy to do. You can also use WebSockets because WebSockets are not tied to the same origin policy as ordinary HTTP requests, or at least that's what I've been told. So you could also use that, say if you want to get rid of some ugly firewalling. You could also implement it in WebSocket, entirely feasible. The encoding of the applications frames is done in H.264 or JPEG if you want. However, keep in mind JPEG encoding is quite a bit larger than H.264, so ideally you would only want to use that on a LAN or something like that. Now, here we have an overview of how a frame of an application travels from the endpoint, or from the application rather, entirely through the browser. As you can see on the right side, we have the pipeline. There are quite a few steps involved, so I will go over them quickly. Unfortunately, not enough time to go through everything in detail. Now, first thing first, when I first started to implement the remote application forwarding, the first thing that comes into mind when you think about showing an application in your browser is video streaming. Browsers support video decoding internally. They do it fast, they do it efficiently. However, in the Wayland protocol, you need to know when a frame is decoded, when a frame is ready to be displayed, and you need to have access to that frame because the Wayland protocol ties a lot of extra states to that frame at the moment it's going to be displayed. And the current solutions, or the built-in solutions in browsers, do not offer that. They don't provide any callback type of when a frame is ready to be displayed, or at least not in such a fine-grained solution. So I had to resolve to a custom video decoder, and that's actually the WebAssembly H.264 decoder you see there. It's actually the Android H.264 decoding library. It's a simple C library actually, compiled to WebAssembly, and it's run inside your browser. The encoding of the applications inside your endpoints happens using GStreamer. GStreamer, most of you probably familiar with it. It's a very powerful, modular, in short, awesome encoding framework. And if we go through the whole pipeline from top to bottom, what basically happens is the application tells the endpoint, I want to commit a frame, I have a frame ready. This frame is basically a handoff to a GStreamer pipeline, which encodes it. And there the first interesting thing happens. H.264 does not support alpha encoding, does not support transparency. Most applications these days, they have some kind of transparency implemented. So we use an OpenGL shader to split the alpha channel from the RGB colors into a YUV color space. And the encoded alpha channel, or rather, the alpha channel is represented as a grayscale image. And both images are then encoded to H.264, one a grayscale, which is actually your alpha, and one that is all the opaque colors. Both are sent over network to your browser, and there WebGL reconstructs those two images together to form again a transparent application frame. So first you receive the image, it's decoded, both images are decoded, you have both the images here, and then you have WebGL that does the color conversion from YUV H.264 originally to RGB, and it also translates then the alpha channel using a WebGL shader to its original alpha value. It's then put into an HTML5 image bitmap, a standard browser concept. It's then written, or rather copied, to an HTML5 canvas. The interesting thing to notice here is that every application on your screen actually consists of two HTML5 canvases. And it uses double buffering to show you a complete and finished picture each time. The main reason for that is that because when you resize an HTML5 canvas, it clears the entire canvas. So if you have to work with only one canvas and we would update its size, you would see a flash of a white canvas before you would see the final image. And in Wayland, the mantra is every frame is perfect. So yeah, we obviously don't want that. So the image is copied to your HTML5 canvas back buffer. A callback is registered in the browser to wait for vsync, which is the request animation frame. And once that fires, the canvases are swapped and you have your final and complete picture in front. once the HTML5 canvas, or rather the frame or the image of the application is shown on screen, the browser sends a command back to the application to say, hey, you can start processing the next frame and start sending me the next frame. And this is basically what is used in classical Wayland to throttle the frame delivery, or the frames per second of your application. Now there are a few gotchas here, or rather a few interesting things to notice. This is a long pipeline, and it's a slow pipeline. Because even if you would have instant encoding and decoding, and you won't have vsync, you still have your network latency. On a slow or network, or definitely the internet, it can be 40-50 milliseconds. So in the best case scenario, you would get 20 frames per second or something. So there is the possibility to actually send this frame callback to your application early on. Because while a frame is traveling down here, and say once it's decoded here, we can also already tell the application to, hey, start rendering your next frame, because, well, the encoding step will probably take some time as well, and you will probably still be busy in the pipeline before I'm finished. The difficulty with this solution is that it's hard to predict the speed of which the frame will travel through the pipeline. If you have a resizing operation where you go from a 640 to a 480 resolution to a full HD, then suddenly the next frame that comes in will be much slower, or the other way around, it would be much faster, and then you would get frame hiccups. So currently it's mostly a theoretical optimization that you could do. Now, we talked about running applications on different hosts, and it's interesting to note here, or rather it has interesting implications, that the compositor does not really know or care where the applications come from. They can run on any different kind of host, which means that they could actually also run inside your browser itself. So we just talked about all the drawbacks that you can have by sending your applications over the network. You have to encode, you have to decode, there is network latency. We can all optimize that so that it's okay to use, definitely in a desktop environment. However, browsers have something called web workers, and a web worker is basically a separate thread or process that runs isolated JavaScript, and it starts from its own file. It has no access to your DOM or to the main thread of your browser. It's a nicely isolated piece that runs inside the compositor sandbox. And its only way of communication is through events. And we can leverage, or we can use that system to actually run Wayland applications inside the web worker. So let's see, we have web workers. They have no network latency, great. They have zero copy data transfers. We can send blobs in web workers to the main thread with zero copy semantics. In short, we have all the good stuff that we have in ordinary native Wayland compositor. And luckily, or quite recently, the browser started implementing off-screen WebGL, which means we can actually render using WebGL inside the web worker off-screen, and use the zero copy semantics to transfer that WebGL rendered image to our compositor. The drawback is that, well, you probably don't want to write OpenGL to write a desktop application. You probably want to have a toolkit on top of that that takes care of that for you. So about half a year ago, I started porting Skia, the graphics library also used by Chrome and Firefox, I believe, to do all their rendering. Google uses it as well inside their Flutter, their new Flutter toolkit. And I ported it to WebAssembly, and it can actually use WebGL to do all the abstract drawings. Google found out, they say, hey, Eric, that's really great what you did. Let's continue with that. And they basically continued that port, or basically did their own stuff, initially based on what I did. And 3 months later, they also announced that they ported Flutter to the browser, surprisingly. Another thing is that we can actually also port existing native applications to, or at least in theory, we can also compile them to WebAssembly if we were to have a libwayland client whose implementation is actually written in JavaScript. Maybe also an important side note, all of this is still a work in progress. So you won't find that in a working condition right now. Just to keep that in mind. And what we end up in essence is a true cloud desktop environment. We can deliver applications to your browser over network, and you could have, say, an account on a website where you log in. That website could have an app store where you can buy applications, and you can then download them in your browser and run them. And if you would tomorrow switch to a different browser, a different machine, you log in and you still have access to those same applications, and you can still run them inside your browser. Because it runs inside your browser, you're not really tied to some kind of machine beneath it. It could be your phone, it could be a tablet, it could be a desktop. Everything runs inside the sandbox of your browser, really. So, but this is still very much future work, very much work in progress. But I definitely hope to present this, or at least give a demo of this work next year in FOSDEM, if I get accepted at least. So let's have a quick demo of what we, or what I did here. Currently, you see, I have here so here on my local machine, I have a compositor running inside my browser, and I also have an application endpoint also running on my local host here. I didn't want to take any risk regarding to firewalls and WebRTC, so sorry, I'm not going to demonstrate a remote application here. But I did manage to get it to work using a cheap Hetzner server at home. And if I were to start, I have here my X terminal. So this X terminal, well, it's X, so it's definitely not connected to the compositor here. And I can start GNOME terminal, and it launches directly inside my browser. And if you can see, if I cannot go beyond. It runs really inside the browser here. It's not subject to any kind of key mapping. The key mapping is handled by the compositor itself. It uses libxkd common, I believe, which is compiled to WebAssembly, and it uses key map files to do all the transferring. And we use you can see, I can just type. Currently, it's configured to QWERTY, as you can see here. And let's have a quick look at the GTK 3 demo application here. So here we have the application, and the performance is relatively okay. As you can see, the frame rate at the top right. Well, yeah, it's a relatively small screen here. If I would run this in full HD on my laptop, I would get around 30 frames per second. If you would run full HD on a cheap Hetzner server with a 40 millisecond delay, the frames per second drops to 8, 9 if you're lucky. But as you can see here, it has no trouble encoding and decoding it just fine. So that's basically it in a nutshell. If you have any more questions, then please do ask.
Can you show us a 3D application?
Sure. So inside here, I think there is an example somewhere. Not seeing it. application, or rather it's a separate frame that's rendered, and it's nicely synchronized with the other surfaces. So if you're familiar with Wayland, this uses a technique to synchronize the updates of all these three separate panes. It's also implemented here, which means that if I would press my space bar and can keep pressing it, then both are nicely synchronized. Quite a challenge to implement, but as you can see, the 3D, it works just fine. There's no issues doing it.
Hands up.
Right. Thank you very much. Thank you for listening.